Video called section 8.1 matrix solutions to linear systems. We're going to learn several operations with matrices and some applications. But before we get to that, we're going to use them to solve systems like we did in chapter 7, but this time with matrices. So just a quick definition, a matrix is a rectangular array of numbers. And remember, a square is also a rectangle, right? Because so if we have a matrix that is a square, that's okay. It's still a rectangle. The numbers inside the matrix are called elements. And here, since we're using them to solve systems, we have a system of 3 equations here and 3 unknowns. And so you can see the coefficients of the x's. We have 3, 1, and 1. And so those are the numbers that you see here on the first column. So we will have the same for the coefficients of y and then the coefficients of z. And when you solve a system to construct an augmented matrix, you have to always make sure that they are in order so that you have all your x's, all your y's, and all your z's. So don't mix and match the variables between columns. And also, the equal sign on the augmented matrix is represented by the line that you see here. And the numbers on the right side of the line will be the constant terms that you see here, 31, 19, and 25. So we're going to study we're going to go over 2 methods. One of them is the Gaussian elimination. Created by Carl Gauss. Gauss Jordan is the other method. And so from there, he got together with this other guy, last name Jordan, and then they created the Gauss-Jordan elimination. So it is like an improved version of Gaussian elimination. So first we will discuss Gaussian elimination, and what you do there, the goal is to have ones on the main diagonal, which is that, and then to have zeros below the ones that you can see there. So that will be Gaussian elimination. And then later on, we'll get to Gauss-Jordan. So the difference with Gauss-Jordan is that everything else will become a 0 as well. We'll do that later. And so once you have your matrix converted into something like that, you could say 1, that was the column that was representing the variable z. So you could say 1z is equal to 4. From there, you could substitute in here and then find what y is, and then you substitute y and z to find x. And so that's how it works. After you have your matrix looking like that, then you use back substitution. Okay, so a matrix with 1s on the main diagonal and zeros below the ones is said to be in reduced echelon form. And on your calculator, that is abbreviated with REF. There's another one that is RREF. And this one here is the one that we will need when we are using Gauss-Jordan elimination. This is just for okay. So what we're going to be doing is to accomplish that, to have our matrix in that form. So remember, ones in the main diagonal, zeros below the ones, and then here we can have any numbers, so I'm just going to put letters And so to accomplish that, what we're going to do is use the matrix row operation. And the following row operations produce matrices that represent systems with the same solution set. So one of those is two rows of a matrix could be interchanged. So underline, highlight, something like that. And that is equivalent to interchanging two equations. Another row operation is that the elements, remember the numbers, in any row, so they may be multiplied by a non-zero number. So you can multiply by a constant that is positive or negative, but not zero. Because if you multiply by zero, the whole equation, you just get zero, right? Number three, the elements in any row may be multiplied by a non-zero number, and then after that, you could add them to another row. And we're going to be doing that in a minute. So that is equivalent to multiplying the same, both sides of the equation by a number. So you don't really change the equation, you just change the way it looks, but you don't change the equivalency. Lastly, two matrices are row equivalent if one can be obtained from the other by a sequence of operations. So as long as you do the same to the whole row, they will still be equivalent. So how do we represent operations, those row operations? So we could say interchange. We could say something like with the R row, R stands for row. In the subscript, it will indicate like what number of the row, right? So if we say the ith row, it would be like Ri interchange with R sub j. If we were talking about like the first and second row, we could say something like R1 interchange with R2. The next one, multiply each element in the ith row by k. K is just a constant here, so we could say k times Ri, or we could say the row and then times the constant. Same thing. So let's say I want to multiply my row 1 times 4. It will just be like that. Or I could say 4R1. Okay, and the third one, you say k times. So we have add k times the elements in row I. So we'll say k times the row. And then we're going to add the corresponding elements. And when we say corresponding, that means that they have to be from the same column. Remember, I told you to order your columns X, Y, Z. So the corresponding elements in row J. So added to RJ. And so that will produce a new RJ. Remember, the subscript, they're just numbers. So, for example, I can say -2 times R1 plus R2, and that will give me a new R2. So that's how it will look like. Okay. Any questions so far? Okay. Are you guys ready? Okay. We're still writing. Okay, so we're going to start with very easy operations just to practice. So we're going to always refer back to the original matrix, okay? So remember, this is R1, R2, R3. So for part A, we're going to switch or interchange R1 and R2. So one thing I like to do is I like to write whatever I'm not changing. So in this case, it will be R3. So -2, -3, 4, and -6. And then the two that I'm going to switch will be R1 and R2. And so this operation sometimes is very useful because when you're trying to solve a system, you have to work by columns, and the first column goes first, right? And what do we need to accomplish first? We need to make that 1. And so that's why sometimes, in this case, the second row already has a 1, and so that's why that operation will be convenient in that case. So we take second row and put it on the first, 1, 2, -3, and 5. And then we take the first row and just write it below. And that's it. Okay, now for part B, we're gonna go back to the original matrix. Okay. And so here we're just gonna change R1 and multiply by 1/3. Since we're not doing anything to R2 and R3, let's just copy them from the original matrix. So from here. Okay, so 1/3 times 3, it will be like 3/3, right? So that equals 2, 1. And then we have 18 times 1/3, so that would be 18/3, which is 6. Then we have -12 times 1/3, so that would be -12/3, which is -4. And then finally, we have 21 times 1/3, so that will be 21/3, which is 7. So in other words, when we multiply by 1/3, we're dividing by 3. Okay, and that's it. We're done with that part. Now let's move on to part C. Now the steps here don't have any sequence, but once we solve a system, they do. So we don't go back to the original. We just take the one that was written like right before. Okay, so now here, going back to the original matrix, we're going to multiply the second row times 2. So for us to do that, I'm going to write it here. Just use like the side of your paper. So 2 times R2. R2 is here, so it's 1, 2, -3, and 5. So that will give me, we have to distribute all across. And so that will give me 2, 4, -6, and 10. And then we're going to add R3. R3 from here. So that's going to be -2, -3, 4, and -6. That will give me 0. 4 minus 3 is 1. -6 plus 4 is -2. And 10 minus 6 is 4. So now to copy the resulting matrix, we're only changing the third row. And it's this. 0, 1, -2, and 4. Our first and second row remain the same as the original matrix here. Like that. Okay, so as I mentioned before, Gaussian elimination is the process of solving systems using matrices. And so the steps are listed here. And so first step is to write the augmented matrix for the system. Yeah. I thought it was yes. Still there. So augmented matrix, remember we need the coefficients on the left, we need the constant terms on the right. And so what we do, we use the row operations that we practice a little to simplify the matrix, and our goal is to achieve this at the end. Ones on the main diagonal, zeros below, like that. From there, we will use back substitution. It's right here. You guys are familiar with it, right? From chapter 7, back substitution. So first, we look at the first column, and we make that one, then we make those two zeros. Once we have that accomplished, we move to the second column, and the first thing we must do is make the 1 right here. After that, we make the zeros. In this case, we only need the 0 below. Once we move on to Gauss Jordan, we will need both, below and above zeros, like zeros everywhere else. Okay, so let's get ready. Yeah, you guys ready? Okay, so first step, we need to construct the augmented matrix. And so that will be, you got to make sure that you have all your x's, all your y's, all your z's, and order, okay? So then you write the coefficients, 3, 1, 1, 1, 1, 3, and then 2, 2, 2, and then we have 31, 29, and 25. Okay. So you guys notice row 2 and row 3 already have 1s. Which one's next? Oh, the second one? Okay, thank you. Yes, that's actually a very useful thing to do after you construct your augmented. Just check that you wrote all the numbers correctly, because if you start wrong, the whole thing will be wrong. So now you notice that our first step will be to make this 3 into a 1. But we could just switch rows to accomplish that. Okay? So what I'm going to do is switch. I'm just going to say R1 interchange with R3. So R1 will be R3. So 3, 1, 2, and 31. Just like that. And now R3 is going to become R1. 1, 3, 2, 25. And then what happened to R2? Nothing. So it stays the same. Okay. And now we're done with that. We have the 1 here. So we're going to write the following, because the first row contains the leading one, R1 is our leading row. Okay, so we're going to use R1 to, what is our next step? Once we have the 1 on the first column, what do we need to get below the 1? Zeros. So we're going to use R1 to make those zeros happen. R1 is good to go, so let's just copy it from the previous matrix. Don't go back to the original, go to the previous. So 1, 3, 2, 25. Okay, now here's the thing. We want to make this positive 1 a 0. So what do you need to add to 1 so that you can get a 0? A negative 1. Very good. And so this is called the additive inverse. So anytime you have to make a 0, you will use that, the additive inverse of the number you're trying to turn into a 0, and multiply by the leading row. So here we're going to change R2, so we're going to add it to R2. And I'm gonna write down my scratch word here. But you guys can write it on the side of your paper if you want. So I would say R1 times negative 1, so it will be this 1, 3, 2, and 25. So that will give me negative 1, negative 3, negative 2, negative 25. And then I'm saying I'm going to add R2. So R2 coming from here, it is 1, 1, 2, and 19. So if I add those two rows, I will get 0, negative 2, another 0, and negative 25 plus 19 will be negative 6. And now we go here. 0, negative 2, 0, and negative 6. Okay, I'm going to erase my scratch work because I need the space. Okay, now our next number that we need to turn into a 0 happens to be a 3. So what do you need to add to 3 to get a 0? Negative 3, right? That's the additive inverse. So we use the leading row, again, R1, times negative 3. And now we add it to R3. So I'm going to multiply, I'm going to do my scratch work here. So we'll have negative 3 times R1. That's what it says here. 1, 3, 2, 4, 5. So that will give me, I have to distribute, remember? So negative 3, negative 9, negative 6, and negative 75. And then we're going to add R3. R3, taking it from here. 3, 1, 2, and 3. No, that's 31. So that would be 0, negative 8, negative 4, and I need your help. Negative 44? Thank you. Negative, wait a second. Oh, that was a series. Thank you, Andrea. So 0, negative 8, negative 4, and negative 44. If you guys catch a mistake, tell me as soon as you catch it. Okay? If we don't catch them quickly, then we'll just be wasting time. Just in case you're wondering why you have to learn to do this by hand, well, because sometimes you will not have a calculator handy. Would you ever have to solve a system of equations using matrices? Who knows? Maybe you won't. Maybe you use it to explain something to your child when he or she is taking Algebra 2. Or maybe you're going to be an engineer who needs to take matrix algebra. And so this is like the first chapter of that class. So now what's our next step? We move to the second column. What's the first thing we must do? Before the zeros, we need to make this negative 2 a 1. So now, since we need negative 2 to be a 1, we multiply R2 times, what do you guys think? What do you need to multiply negative 2 to give you a 1?
1 over negative 2.
1 over negative 2 or negative 1/2, same thing, right? So if we do that, we will get positive 2 over 2, which is 1. And so that's what we're going to do. We're going to use and this is called the multiplicative inverse. And so that will be negative 1/2. So anytime you are trying to make a 1, you will rely on the multiplicative inverse. And when you're trying to make a 0, then you will rely on the additive inverse. Okay, so R1 and R3 will remain the same, so let's just copy them from here and here. Okay, and we're saying R2 times negative 1/2. So we'll have 0 times negative 1/2 is still 0. And then we have negative 2 times negative 1/2. We already said that was 2 over 2, which is 1. Next number, 0 times negative 1/2, still 0. And the last one, negative 6 times negative 1/2, that would be positive 6 over 2, which is 3. So you guys start seeing the light at the end of the tunnel, right? Kind of. In fact, this problem is already telling me one solution. What is 3?
Y.
That's correct. So you get a card for that. Okay, so now we're done with the 1 here, right? So now R2 is our leading row because it contains the leading 1. So let's just copy R2 because nothing will change to it. So 0, 1, 0, and 3. So now let's look at this negative 8. What are we supposed to make this negative 8?
0.
A 0. So we're going to use R2. Now R2 is our leading row. That's why we use R2. R2 times, what is the additive inverse of negative 8? No. Did you say 1 over negative 8? No. That will be the multiplicative inverse. I want the additive inverse, positive 8. So that plus R3. Remember, you have a negative 8. What do you need to add to it to get you a 0? Okay. And then R1, we're not going to change it anymore because we're just going to do the Gaussian elimination. Okay, so negative 8, not negative 8, positive 8 times R2 from here, 0, 1, 0, and 3. That will give me 0, 8, 0, and 24. And then I'm going to add R3 that is coming from here, from the previous matrix. And that is 0, negative 8, negative 4, and negative 44. That will be 0, 0, negative 4, and that will be negative 1. So that is my new R3. At this point, we will use back-substitution. And so, oh, not really.
Yeah.
Oh. What is left for us to do?
You have to multiply row, well, the new row 3 by negative 1 over 4.
Correct. So now we need to multiply R3 times, you have a negative 4. So you have a negative 4 over 1. What do you need to multiply by to get a 1? That will be negative 1/4. So that's what we use here. We're almost done, I promise. I'm going to copy R1 and R2. Okay. So once you have zeros, it becomes like a lot easier because, you know, anything you multiply by 0 will still be 0, right? So 0 times negative 1/4, 0. 0 times negative 1/4, 0. And then negative 4 times negative 1/4, that's a 1. And then negative 20 times negative 1/4, if you're not sure, just write them down. There's nothing wrong with that. You do not need to use decimals. You can do fractions. So that's positive 20 over 4, which is 5. Okay, so now we're done here, 5. Now we're going to use back substitution. So we have 1. Remember, we have the order x, y, and z. So we have the equation that says 1z is equal to 5. We also have 1y is equal to 3. And then from here, we have the equation 1x plus 3y plus 2z is equal to 25. So we're going to use the back substitution method. So it will be for x plus 3 times 3 plus 2 times 5 equals 25. And then we need to find x.
6.
Very good. So don't forget those numbers. We're going to see them again in a few slides. Okay, so those are the three solutions. X equals 6, y equals 3, z equals 5. I know it's like kind of like a tedious problem, but like the more you do it, the faster you get at it. All right, so that is your side for you to do on your own. I'm just kidding. We're gonna skip that.
Can you show us? Nice, can you show us?
I will run out of time.
No, the calculator. Let's do it, the calculator.
Oh yeah, I'll show you guys at the end of class. Actually, no, I have a video that shows that on my YouTube channel. I really do. How to solve matrices on the calculator. Okay, so now let's move on to the other method, the Gauss-Jordan method. Come on, Jerm. And so the Gauss-Jordan elimination, let me find the page. Called after Carl Friedrich Gauss, and what's his name? I always forget his first name.
Jordan.
No, Wilhelm.
Michael Jordan.
Not that one. Jordan was his last name. So as you guys can see, the life expectancy back then was not that high. So what they did, they got together and they improved the method, right? And it continues the process until you have ones down the main diagonal again. And zeros elsewhere. And such a matrix is said to be in reduced row echelon form. On the calculator, that will be the one with the double R, R-R-E-X. And the word echelon is comes from a Greek word that refers to the stair pattern. So you guys can see that. All right, so the steps are the same. You start writing your augmented matrix, and then you work on getting the ones first. You start with the first column and finding that one. Then you move on to make your zeros. After that, you move to the second column, you make your one, and then your two zeros. After that, you move on to the third column, you make your one, and then your two zeros. And at the end, you get something very simple, such as here will be Z equals the letter C, represents the number. The variable Y, here, 1Y, equals b. And 1x, because remember this is the x column, 1x is equal to a. So then there's no need to do back substitution. That's the difference. That you just get all done. I personally I prefer this one because it's like you just get it all done. Okay. Now it is very easy to do this on the calculator. We know that. But on your take-home exam, I am going to be very picky about when I grade those problems. So you still need to show me some understanding. Okay, so this problem, the system, happens to be the same one that we had before. And so we're just going to continue from where we left off before doing the back substitution. Let's see. Okay, so it was something like 1, 3, 2, 25. And then we have 0, 0, 1, 0, 1, and a 5. Right? And a 3. Okay. So what I want to do first, what I want to do first is we have this 1, right? We already have a 0. What do we need? Another 0 above, right? Because remember, we're doing the Gauss-Jordan, the one that has 1s across the main diagonal and 0s everywhere else. So we're going to use R2 times the additive inverse of this 3, which is -3, and add it to R1. And so that will be, well, let me copy my other 2 rows that I already have. 0, 0, 1, 5. And then I have 0, 1, 0, 3. Okay. So R2 times -3 will be -3 times 0 is 0. -3 times 1 is -3. -3 times 0 is 0. And -3 times 3 is -9. And then we're going to add row 1. Row 1 from here. And that is 1, 3, 2, 25. Did we do something wrong? Okay. So this will be 1, 0, 2. Oh no, it's okay. And this is 16, correct? Yeah? Okay, we're almost there. And now what's left for us to do is we already have our 1s across the main diagonal, correct? We have 0s almost everywhere except for here. So now to get rid of that 2, make it a 0, we're going to use this 1 because it's in the same column. So now our leading row is R3. And what is the additive inverse of 2? -2 plus R1. So let's just copy R2 and R3. Okay, so -2 times R3. It's going to be -2 times 0, 0, 1, and 5. That will give me 0, 0, -2, and -10. And then I need to add R1. R1 coming from here. So that will be 1, 0, 2, 16. 0 plus 1, 1. 0 plus 0, 0. -2 plus 2, 0. -10 plus 16, 6. So 1, 0, 0, 6. And here we get no need for back substitution. You just get that 1z equals 5. 1y equals 3. And 1x equals 6.
Wow.
And which is the same answer that we got before, right? Okay, so this is the end of the video.
Can I get my card?